This is problem G, and it says an electron collides elastically with a stationary hydrogen atom. The mass of the hydrogen atom is 1,837 times that of the electron. Assume that all motion before and after the collision occurs along the same straight line. What is the ratio of the kinetic energy of the hydrogen atom after the collision to that of the electron before the collision? So basically not basically, but what they're asking for is, what is this ratio, kinetic energy, the final kinetic energy of the hydrogen atom, so H, after the collision, to the original kinetic energy of the electron before the collision. So kind of a complicated formula. Okay, so I'm going to write this out here. Let's first see what we actually got. We actually don't have a velocity given for the electron. I just pulled it off my physics simulation software, and I just made an animation in there. And actually, it's not much telling in there. Let's see. So let's assume that we do know the mass of the electron. We can look it up in the back of the book. That also means that we know the mass of the proton, and they want to know, what the ratios of the kinetic energies. Overall, actually, we may or may not need the original velocity or the final velocities. Okay, let's see. We're going to write this one down here. So this one is 1/2 the mass of the hydrogen times the final velocity of the hydrogen squared, divided by 1/2 the mass of the electron, VOE squared, the original velocity. Here, of course, the 1/2 here would eventually divide. This one here, this ratio, we know. They told us it's 1,837, and so which means we just have to determine this ratio here. Well, that ratio we can get from the conservation of momentum. So where we're going to write before and after. So before, we only have the electron, so I'm going to write this here instead of m1, I'm going to write it as me minus, I guess, times its original velocity of the electron, and that equals the mass of the electron after the collision plus, of course, that negative here only goes to the index here of the electron, just indicating it's a negative charge electron. So plus mass of the hydrogen atom times its final velocity. Okay. Now at this point here, it already gets interesting. We have the original velocity of the electron here. We have the final velocity of the hydrogen here, and they appear here and here and here, but now we have a third velocity for the electron. So all of a sudden, instead of two variables, the ratio of two variables, we have actually three variables involved here. So it gets a little bit too much. Well, remember that it says in the problem it's an elastic collision, and because it's elastic, that's also why I didn't combine them on the right hand side, because they're not going off together. So that's why I kept them separate. But because it's elastic, the kinetic energy is also conserved. In an inelastic collision, some kinetic energy is being converted to something else, usually heat. And so this is how I would write this. Squared, and then the same thing on the right hand side. Squared. I shouldn't have done this little negative there all the time. I don't know if I can erase this. There, it kind of seems a little bit too confusing. Yeah, I think that looks a little better here if I don't write that little negative at all times. There, I think I got it. Yeah, okay. So plus 1/2 mass times VFH. Okay, squared. Okay, what happens here, because now we have two equations in apparently three variables, if we combine them, we can throw one of the variables out and we're just left with two variables. It still sounds quite a bit. We still have two variables left after we combine those two, but at least we can form them into some ratio somehow. At this point, the algebra here becomes quite involved, and you would be required actually to know how to do the algebra since you're in this physics class. However, there is a shortcut to it, and that shortcut is in the book in example 7 in this chapter 7, where they have an example for an elastic collision, and here's what they come up with. They say, okay, the final velocity of the hydrogen after the two equations have been combined for an elastic collision is 2 times the mass of the electron divided by the sum of the masses. This is not to say that the two combine, this is just that the algebra yields this one here as the ratio for the velocity times the velocity of the electron. Well, here we have a ratio which I'm sure we could use here. So, in going on with the algebra, here's what I'm gonna do. Yep, need some more space. So I'm gonna have still that ratio up there, the kinetic energy ratio, KE ratio, I guess I call it. Is gonna be the 1/2 is already gone. So mass hydrogen divided by mass electron. And then I think I pull it down just a little bit so we can still see that. So yeah, I just said the 1/2 is gone, and here is mass hydrogen divided by mass electron, and then times the square divided by the square of the two velocities. So I square everything, and then I divide by the square of that electron velocity. But this one here gets squared as well, so I'm going to have 4 times mass of the electron squared divided by mass of the electron plus mass of the hydrogen squared. So here what we can do is, of course, one of the electron masses divides here, and then pretty much what we can do here is just say, okay, the mass of the electron, we just call it 1, and then the mass of the hydrogen atom, we call it 1837. Plug in the numbers, and we're going to come up with a ratio. Notice that you have 1837 up here, but down here you also have it squared, and that means you come up with a pretty small number in the neighborhood of like 10 to the negative 3 as the ratio. I made a little animation for this, and I gave the electron an original kinetic energy of 1000 joules. Okay, that's not true, of course, but I just chose one example here, and notice that if this had 1000 joules, then this comes out to only 2 point some joules, which means a neighborhood of 0.002 something. And if you calculate that ratio, that's actually really close here what I got in the animation. By the way, I looked this up, electron-hydrogen collision, when we study nuclear physics, atomic physics, and quantum mechanics. That's usually not a collision that occurs, and I couldn't really find much of it. There are certain effects going on in here. You know, what actually does the electron do? It's not just rebounding from the hydrogen, but what actually is it doing? Is it reacting with it, or what have you, being captured or something?